Okay, welcome to week 2, lesson 2. This is the second lecture on reaction types. We're going to be considering the insertion and elimination reactions. Much like oxidative addition and reductive elimination, insertion and elimination are microscopic reverses of each other. So everything we learn about the insertion reaction, we will also know about the elimination reaction. Before I go any further, I want to remind you that you should take a look at Week 2, Homework 3, the guided inquiry on the insertion reaction before viewing this video. So if you haven't done Homework 3 yet this week, please stop the video now. Go and give your best shot at doing the homework and then come back here and we'll talk through it. Okay, so I think you know the drill by this point. We're going to look at the various metrics for the starting material and product of this reaction, looking at coordination number, oxidation state, DN count, valence electron count, and you should also be able to do CBC notation for these complexes. So think a little bit about what the starting material and product are, and then I'll post it as the next part of the video. Okay, hopefully you got coordination number of 6 for both compounds, oxidation state of 1 for both compounds. They're both D6, they're both 18 electron compounds, and so what we can see is there is no change in coordination number, oxidation state, DN count, or valence electron count. Very different reaction from oxidative addition. Also, both compounds are manganese L5X complexes. Okay, so in the guided inquiry, we had you looking at a variety of these possible mechanisms. So if we look at the insertion or addition of a C13 labeled carbon monoxide to this manganese pentacarbonyl methyl complex, we expect to form the acyl product. And there are 3 sort of reasonable possible mechanisms for this reaction. Alkyl migration, and that's the reaction where the methyl group moves to the carbonyl. Sorry, the methyl group here would move to an adjacent carbonyl, so any of these 4 carbonyls in the cis position. A direct insertion would be where the carbonyl ligand, the external ligand, actually directly inserts into the metal carbon bond. And carbonyl migration would be where one of the cis carbonyls slides over and inserts into the metal carbon bond. All 3 of these mechanisms give different possible product distributions. So if we look at the alkyl migration mechanism, what we would expect to see is this product distribution where we have a product where the acyl is cis to the C13 labeled carbon monoxide that comes in axially. If we had a direct insertion mechanism, we would expect to only form the C13 labeled acyl. And if we had the carbonyl migration, we would again expect to see the C13CO cis to the acyl ligand. This reaction, the reaction of manganese pentacarbonyl bromide with C13 labeled CO, does not rule out the top or the bottom mechanism, but it does rule out the direct insertion. We don't see that mechanism, we don't see that product, so at least on the time scale of the reaction, we're not seeing that product, and we don't believe that that mechanism is taking place. This is, however, an example of negative evidence, because the fact that we're not seeing a product doesn't mean that it can't happen that way. It just might be a lot slower or on a different time scale, or it goes that way and then reverses rapidly. So it might be an equilibrium with a low equilibrium constant. So negative evidence is not ideal, but sometimes it's all you can get. There's one important additional point I'd like to make about these experiments, and the authors did this experiment. They did not ever observe any redistribution of the products after they were formed. So for example, this C13 labeled cis to the acyl group, if they took that complex and subjected it to the reaction conditions for a long period of time, they didn't see a rearrangement of the C13 label to this position or this position. I guess you wouldn't actually be able to tell these 3 positions, but you never saw the trans label in the compound. So once you form the complex, it's stable and it doesn't rearrange anymore, and that's crucial for the success of this experiment. Okay, now let's look at the next experiment. So this time they started with the C13 labeled pentacarbonyl manganese methyl complex with the C13 label cis to the methyl, and they treated that under an atmosphere of regular C12 carbon monoxide. So looking at the alkyl migration mechanism, we would expect a product distribution that looks like this, where we see a 1 to 2 ratio of products. So 1/4 of the time, this methyl group would migrate to the C13 label, making the C13 acyl. We see that 1/4 of the time. 1/4 of the time, it would migrate to this carbon monoxide, which is trans to the label. And then 50% of the time, it would migrate either here or here, which are indistinguishable positions in this experiment. And so we would see 2 molar equivalents of that product. Now let's look at the direct insertion. The direct insertion, again, gives us the only one possible product. The external C12CO would come in and insert directly into the manganese carbonyl bond, giving us the C12 acyl as the only possible product. The third reaction would be carbonyl migration, and we would see this product distribution. So what's happening here is 1/4 of the time, this C13 labeled CO would migrate into the manganese methyl bond, giving us this C13 labeled acyl in 25% of the product. And then the other 3 carbonyls could migrate, giving us the C12 labeled CO, and that would be 75% of the product. This experiment rules out 2 of the possible mechanisms. We in fact see a 1 to 2 product distribution, so that rules out the direct insertion and the carbonyl migration mechanisms. You might argue, and it's reasonable, that maybe the 1 to 2 ratio that you propose to see and the 1 to 3 ratio that you see for the carbonyl migration, maybe you could expect that there might be some error in the experiment and the 1 to 3 ratio is what you're actually seeing. So it would be good to do additional experiments, and the authors did that. So the authors carried out this third experiment. They carried out other experiments too, but this is the one that we'll stop with. And this is the reverse reaction, where they're looking at the decarbonylation of this C13 labeled acyl complex. So an important point to note here is that the principle of microscopic reversibility. If you have a reaction that goes in the forward direction by one pathway, then it has to go backwards by the same pathway. There's only one lowest possible energy starting at Harvey Mudd, going over Mount Baldy to get to the desert north of the mountain range. There's one lowest energy pathway forwards, there's one lowest energy pathway backwards. And so mechanistically, the reactions go by the same path. And so the products that they observed doing this reaction was, again, a 1 to 2 ratio of the alkyl migration. So this, instead of looking at alkyl migration, they're looking at the deinsertion. So what has to happen here is one of these 4 axial carbon monoxides has to leave. 25% of the time you'll lose the label, and when you lose the label, the methyl group will migrate to that position. So 25% of the time we'll have an unlabeled manganese pentacarbonyl bromide. 25% of the time we'll lose this carbon monoxide, and the alkyl group will migrate to that position, giving us the trans C13 label to the methyl group. And then 50% of the time we'll lose one of these 2 COs. The methyl group will migrate to those 2 positions, and we will get the cis C13 label. In the direct insertion mechanism, so in this case the direct deinsertion mechanism, we would expect only one product, and that's where the carbon monoxide that's present in the acyl group deinserts out of the molecule, leaving only one possible product. The final mechanism, the carbonyl migration mechanism, which, looking at the deinsertion, would give us this product distribution. So what we're seeing here is 75% of the time you're losing one of these unlabeled carbon monoxides. The acyl carbon monoxide migrates back to that position, and you get the C13 labeled cis to the methyl group. And then 25% of the time you lose this CO. The CO migrates down, and you have this manganese pentacarbonyl bromide product. When the authors carried out this study, they saw a 1 to 2 product distribution, which rules out these lower two mechanisms again. And so it really seems to be stacking up where alkyl migration is the mechanism of choice in this manganese pentacarbonyl methyl situation. And that is believed to be true. And so people now know that the mechanism of this reaction is always alkyl migration. So here's an iron example. So this CP iron triphenylphosphine carbonyl ethyl complex can also undergo a carbonyl insertion mechanism. And so what they see is that the ethyl group migrates to the CO, leaving this empty coordination site, that's an orbital, and then it is trapped with external carbon, C13 labeled carbon monoxide. So this is a chiral iron complex. They resolved the iron complex and then looked at the stereochemical outcome, proving that the alkyl migration mechanism holds in this case. You've been in my class long enough now to realize, though, that it's not going to be that simple. Inorganic chemistry is never that simple. And if you change the solvent from nitromethane to HMPA, it turns out that you see a reversal of the reaction where in the more polar solvent, the carbon monoxide migrates to the ethyl, leaving the empty coordination site here, and the C13 label ends up here. Those two molecules are enantiomers of one another, and they were able to determine that by optical rotation measurements, among other things. So it turns out that you can see carbonyl insertion or alkyl migration as the mechanism for the migratory insertion reaction. It wasn't until about 10 years ago that there was any really good direct evidence for a direct insertion mechanism. Elon Eisen has studied this reaction in quite a bit of detail. I'm not going to go into a lot of details here, but there's plenty of experimental and theoretical evidence that suggests that this carbon monoxide ligand directly inserts into the alkyl, giving the acyl product in this rhenium complex. If you look at the entropy of activation, it's an extremely large negative number, suggestive of a very organized transition state for this reaction. And they also did kinetics, and so the kinetic rate law for these reactions is very simple, and for a two-step process they have a much more complicated rate expression, and they have been able to show that this mechanism is really the only well, certainly the first example of a direct insertion mechanism for carbon monoxide into an alkyl. The carbonyl insertion reaction, or the migratory insertion reaction, is considered a 1-1 insertion because the metal and the carbon that the carbonyl inserts into both end up on the same carbon. Contrast that to olefin insertion, where if you take a metal hydride and add ethylene, so first, the ethylene can coordinate to the metal. That pre-activation is important for the reaction. It sort of sets it up to do the next reaction. And then the hydrogen ends up on carbon 1. The metal ends up on carbon 2. So this is known as a 1-2 insertion, where the metal and the group that was on the metal are now 2 carbons apart, where comparing that to the carbonyl insertion, the metal and the hydrogen, or the metal alkyl, end up on the same carbon. That's a 1-1 insertion. The reverse of this reaction, so in the carbonyl insertion reaction, the reverse was the carbonyl deinsertion. The reverse of this reaction is the beta hydrogen elimination. So this hydrogen is on the alpha beta carbon, and when you do a beta hydrogen elimination, you form the metal hydride and an ethylene complex. So an elimination reaction is the microscopic reverse of an insertion. An agostic interaction is a trapped beta hydride elimination, which I'll show on the next slide. So you can have both alpha and beta agostic interactions. This is shown in the textbook chapter. But here we have a hydrogen that is on an alpha carbon, and for some situations where there's an empty orbital on the metal and it really wants some additional electron density, you can actually severely distort this group. You would normally expect 120-degree bond angles around that carbon. You would expect sort of a normal CH bond. But what happens is that the CH stretching frequency drops from 2600 down, drops to 2600 from around 3000 wave number. So that CH bond is weakening because this CH bond is donating into the empty orbital on the metal. You can also see this in the CH coupling constant in the carbon NMR spectrum. And so the angle here, this metal carbon hydrogen angle can be approaching 90 degrees. A beta agostic interaction is shown here in this crystal structure data. So we have the titanium, alpha carbon, beta carbon, the hydrogen on the beta carbon. And so this is extremely distorted carbon. So that's instead of 109 degree tetrahedral bond angle, that's opened up to about 120 degrees. This angle is very acute. And so you again see spectroscopic and structural changes in the molecules as it undergoes this additional interaction with the metal center. The beta hydrogen elimination is so important because it means that metal alkyls that have beta hydrogens aren't very stable. I mentioned in the history slide that the ferrocene, the discovery of ferrocene really launched the field of organometallic chemistry. People had looked for metal alkyls before, but they were not ever stable, and that's because people tried to make things like metal ethyl compounds, which have a lot of beta hydrogens, and those beta hydrogens underwent the beta hydrogen elimination reaction, and they were unstable. They decomposed. These molecules have beta hydrogens, so there's 2, 4, 6 beta hydrogens in the 1 adamantyl group, 2, 4, 6 in the norbornyl, and this alkyl does not have a beta hydrogen. The slide is a lie. So why did these two molecules have stability when they undergo the beta hydrogen elimination? Why don't they undergo the beta hydrogen elimination? And it's because if you were to do the beta hydrogen elimination, you would have to remove a hydrogen at this position here. If you did that, you would form this double bond. That's known as a bridgehead double bond. It's extremely unstable. This part of the double bond is sort of rotated in and out of the board. This one is in the plane of the board. It's really unstable, and so that bridgehead double bond prevents the beta hydrogen elimination from taking place, so we don't see it. These 3 alkyls have no beta hydrogens. They are very common ligands in organometallic chemistry. Neopentyl, trimethylsilomethyl, neophil, and benzyl on the previous slide. These alkyls which don't have beta hydrogens are quite stable, and they allow you to make metal alkyls and study their properties quite easily. An important process related to the field of insertion and elimination chemistry is polymerization, plastics. So polyethylene, polypropylene, polystyrene, these are all molecules that are made by polymerization, and they're usually metal catalyzed, not always. And so if we consider a zirconium hydride reacting with ethylene to form polyethylene, we would eventually form a zirconium alkyl group, and we can continue. The first insertion would give us that ethyl group, and then we could make a butyl group and then a hexyl group. And so we're slowly inserting ethylenes. And so the textbook chapter goes into the thermodynamics of this reaction, and I won't go into it in a lot of detail right now, but I want to at least think about it and set up the problem. So think about, in this first reaction, what bonds do you need to break and what bonds do you need to form in order to do an insertion of ethylene into a zirconium hydrogen bond? I would argue that you've got to break the zirconium hydrogen bond, so the metal hydrogen bond, and you've got to break the carbon-carbon double bond. You're going to end up forming the metal carbon single bond and the carbon hydrogen single bond. So we have to break these 2 bonds, and there are their energies. We have to form these 2 bonds, and there are their energies. And so we could then calculate the enthalpy of that step and determine how favorable it was. You could also do the same thing for insertion into a metal alkyl, so the second step of the polymerization reaction, and those are the numbers that you would use. So for insertion of a ethylene into a zirconium hydrogen bond, we have a minus 8 kcal per mole energy difference, so that's thermodynamically favorable by 8 kcals per mole. Insertion into a metal carbon bond is also favorable, although less favorable. So this is how we can rationalize the fact that the polymerization reaction can take place. And the book goes through an example of why we don't expect deinsertion, breaking the carbon-carbon bonds to reform the metal hydride. That seems to be an unlikely chemical reaction. So this is just an example of a large industrial use of insertion chemistry, polymerization, and these types of reactions are used industrially all the time. We'll start looking more into that in the next lecture when we start talking about catalysis.